Somewhere off the coast of the United States, two shorelines stare at each other across miles of open, churning ocean. For 100 years, the only way across has been by boat or by plane. But what if you could drive or ride a train straight through the middle of the sea itself? Not under it in the dark, the way we do today. Through it, in the light, with the ocean pressing in on every side, visible, alive, and endless. This is not a real funded project. There's no ground broken, no contractor selected, no ribbon waiting to be cut. This is a speculative engineering concept. A what-if built the same way NASA engineers sketch Mars habitats before a single rocket leaves the pad, with real materials, real physics, and real constraints. Call it a thought experiment in concrete, steel, and glass. We're calling it the glass tunnel, and by the end of this video, you'll understand exactly how something like it could be built, and why nobody has done it yet. Part 1. Why we don't already have this. Humanity has crossed water with bridges for thousands of years. We've also gone under it. The Channel Tunnel between England and France, opened in 1994, proved that boring through rock beneath a seabed is not just possible, it's routine if brutally expensive. Japan's Shinkansen Tunnel, the longest undersea rail tunnel on Earth, has carried trains beneath the Tsugaru Strait since 1988. In the United States, the Chesapeake Bay Bridge Tunnel does something similar on a smaller scale, ducking underwater specifically so it doesn't block shipping lanes. All of these share one thing in common: they're dark. A rider on the channel sees nothing but tunnel wall for 20 minutes. That's fine for a commuter. It's not exactly inspiring. So here's the question this concept tries to answer. What happens if you take the engineering playbook that already works? Reinforced tunnel boring, pressure-rated linings, rail beds, ventilation, drainage, and swap out the boring, opaque middle section for something transparent, something that turns a commute into an experience? The short answer is, it's staggeringly hard, but not impossible. The ocean does not care about your ambitions. At depth, water pressure increases by roughly 1 atmosphere, about 14.7 pounds per square inch, for every 33 feet you descend. A tunnel sitting 300 feet down isn't fighting against a gentle push. It's holding back roughly 9 times atmospheric pressure all day, every day, for decades without a single failure. That's the design problem in one sentence. Part 2. Picking the site. Every undersea structure begins the same way real infrastructure does in America, with years of quiet, unglamorous survey work. Before a single barge shows up, geotechnical teams need answers to a short list of very expensive questions. How deep is the water along the proposed route? What does the seabed actually consist of? Is it solid bedrock, soft silt, loose sand, or a mix that shifts with the seasons? What do currents do at different depths, and how do storms change that? Is the corridor anywhere near a fault line, and if so, by how much? In our concept, engineers deploy the same toolkit the offshore wind and oil industries already use: multi-beam sonar survey vessels mapping the seafloor in 3 dimensions, autonomous underwater vehicles crawling the bottom at walking pace, geotechnical drilling rigs pulling core samples from dozens of points along the corridor, and moored buoys tracking current speed and direction across entire tidal cycles. This isn't a season of work, it's years, and it has to happen before an engineer draws a single support beam, because the seabed itself is the foundation. Build on the wrong strip of silt, and no amount of steel saves you. Part 3. The boring bookends. On each shore, construction starts exactly the way it does for any major American infrastructure project, with dirt, cranes, and a lot of concrete. Reinforced approach tunnels are excavated from both coastlines, angling downward toward the sea floor. These sections look almost nothing like the flashy transparent tube everyone's picturing, because they aren't meant to. They are the rugged workhorse of the whole system, precast concrete lining, dense steel rebar reinforcement, waterproof membrane layers, rock bolts anchoring the tunnel to surrounding stone, ventilation shafts, drainage sumps, and emergency egress passages. Modern tunnel boring machines, the same class of machine used on projects like Seattle's Alaskan Way Tunnel or New York's 2nd Avenue subway, would grind through rock and sediment a few inches at a time, lining each freshly cut section with precast concrete rings as they go. It's slow, it's loud, and it's the least photogenic part of the entire project. It's also the part that has to be closest to perfect because everything else connects to it. Part 4. Building the impossible part. Here's where the concept leaves familiar territory. The transparent mid-ocean section isn't built in place. It's built on shore in massive dry dock fabrication facilities, the same way shipbuilders assemble super tankers or offshore oil platforms, piece by piece, tested repeatedly, then floated out only once it's proven. The shape matters enormously. A round cylindrical cross-section isn't a stylistic choice, it's physics. A circle distributes external water pressure evenly around its entire circumference, the same principle that makes submarine holes round instead of boxy. A rectangular tube would need dramatically thicker, heavier walls at the flat panels to resist the same pressure, and even then it would be more prone to stress concentration at the corners. Round wins. Each tunnel segment in this concept is built from a series of circular structural rings. Imagine them machined from a titanium alloy chosen for its exceptional strength to weight ratio and its resistance to saltwater corrosion, a real problem that has plagued offshore structures for a century. Between those rings, curved, multi-layer laminated glass panels are set into machined grooves, similar in principle to the laminated acoustic and pressure glass already used in submarine viewports and public aquarium tunnels, just enormously scaled up. Real aquarium tunnels already do a small version of this. The tunnel at Georgia Aquarium in Atlanta, for instance, uses thick acrylic panels to hold back hundreds of thousands of gallons of water above visitors' heads. Our concept scales that same idea from a shallow indoor tank to open ocean at real depth, which means far thicker laminated panels, far more rigorous pressure testing, and a fundamentally different order of engineering margin. Each seam between glass and metal gets multiple layers of sealing, waterproof polymer gaskets compressed under controlled pressure, followed by a secondary chemical sealant as a backup layer, because in undersea engineering you never rely on a single point of failure. Every system doubles up. Part 5. Testing before trust. Nothing goes into the ocean until it's been broken in a lab first. Figuratively, ideally, not literally. Each finished tunnel segment in this concept is placed into a test cradle and subjected to pressures exceeding what it will ever experience at its actual installation depth. Engineers pump water against the outer shell, monitor for flex and deformation with strain gauges, check every seam with acoustic leak detection sensors, and run the segment through repeated pressure cycles to simulate years of tidal stress compressed into days. This mirrors real-world practice. Submarine hulls, deep-sea research submersibles, and offshore pipeline sections all go through comparable pressure cycle testing before deployment, because the cost of a failure at depth is measured in lives, not just dollars. Only a segment that passes every test moves on to transport. Part 6. Lowering glass into the ocean. This is the part of the concept that looks the most like science fiction and is, ironically, the part closest to things we already do. Offshore construction crews already lower enormous structures onto the seabed for wind farms, oil platforms, and pipeline anchors. In this concept, floating cranes position each finished glass and titanium segment above its prepared foundation. Anchor bases already poured and protected with scour-resistant rock armor to stop currents from undermining them. remotely operated vehicles, the same kind used routinely by the offshore energy industry, guide the descent with lights and manipulator arms, watching the segment settle into alignment grooves on the seabed. Hydraulic clamps lock it down. Only once it's fully secured to the crane cables release. Then it repeats, segment after segment, lowered, aligned, sealed against its neighbor with compressed gasket rings, pressure tested again at the new joint and verified by sensor before the next one goes in. Slowly, a continuous corridor takes shape along the seafloor, visible from above as a faint glowing line beneath the waves. Part 7. Making it a transit system. A tube full of glass isn't a transportation system yet. It's just a very expensive fish tank. In this concept, transition zones between the concrete approach tunnels and the transparent segments get heavy-duty flood doors. The same category of safety system used in real subaqueous tunnels today, designed to seal instantly if a breach is ever detected anywhere along the route. Drainage channels and sump pumps tie into the tunnel's low points, power conduits, fiber optic communication lines, ventilation ducting, fire suppression systems, leak sensors, and structural monitoring cameras get threaded through the entire length. The rail bed itself sits on vibration isolation pads, a detail borrowed directly from real high-speed rail engineering, since a tunnel this long needs to dampen vibration to protect both the structure and the ride quality. Rails go down, get aligned to sub-millimeter tolerances, and get wired into a centralized signaling system. Before a single passenger boards, the tunnel goes through the same staged commissioning process any major transit project uses. First, an unmanned inspection vehicle crawling the entire length at low speed while sensors log vibration, alignment, and structural response. Then empty test trains running for months, proving out signaling, braking, emergency systems, and the flood doors under real operating conditions. Only after that does a project like this ever see a paying rider. Part 8. The ride. Assume it all works. Assume years of survey work, fabrication, testing, and commissioning are behind it. What does the actual experience look like? A rider steps aboard a train that looks from the inside almost exactly like modern high-speed rail. Comfortable seating, quiet cabins, standard boarding. Then the train descends toward the coast and enters the tunnel mouth. For a few minutes, it's a completely ordinary tunnel ride. Concrete walls, tunnel lighting, the low hum of rail on track. Then the walls change. The train enters the transparent segment and the concrete gives way to curved glass and titanium ribs lit from below with soft blue lighting designed to avoid glare against the darkness outside. Beyond the glass, open ocean. Depending on the route and depth, that might mean drifting light through shallow water, schools of fish moving past the windows, or at greater depths, simply the vast quiet blue-black of the deep sea broken only by the tunnel's own lighting. It's not a roller coaster, it's closer to a moving aquarium exhibit crossed with a subway commute, the kind of experience that turns "I have to get across the water" into "I want to get across the water." Part 9. Why this isn't being built tomorrow. Every concept video eventually has to answer the boring but essential question: so why doesn't this exist? Cost is the obvious answer, and it's a big one. The Channel Tunnel, built with conventional dark tunnel technology and no transparent sections at all, cost roughly the equivalent of over $12 billion in today's dollars and took 6 years to build. A transparent undersea tunnel would multiply that cost significantly. Pressure-rated structural glass at this scale doesn't have an existing supply chain, and neither does mass-produced titanium ring fabrication at these dimensions. Every first-of-its-kind component means custom engineering, custom testing, and custom risk. Maintenance is the quieter problem. Marine growth, biofouling, and corrosion never stop. A concept like this would need a permanent fleet of maintenance robots and dive teams cleaning and inspecting glass panels indefinitely, adding an operating cost that never goes away. And then there's simple engineering conservatism, which in infrastructure is usually a good thing. Nobody wants to be the first agency to greenlight a 9-mile aquarium tunnel under open ocean. The technology to attempt it may exist in pieces. The willingness to bet billions of dollars and public safety on assembling those pieces for the first time at this scale does not yet exist, and arguably shouldn't until smaller scale precedents prove the concept in stages. None of this exists. Not the surveys, not the fabrication halls, not the glass rings resting on the seafloor. It's a concept, an exercise in taking real tunneling technology, real pressure engineering, and real transit systems, and asking how far they could stretch if cost and caution weren't standing in the way. But every piece of this idea already exists somewhere in the world in a smaller form. Aquarium tunnels already hold back water over people's heads. Submarines already survive crushing pressure at depth. Offshore crews already lower enormous structures onto the seabed with millimeter precision. Tunnel boring machines already carve rail lines under real oceans. The glass tunnel isn't science fiction. It's several proven technologies, imagined at a scale nobody has attempted yet. And that gap between what's technically possible and what's actually been built is where almost every great piece of infrastructure starts.